Awesome, thank you. Welcome everyone to the Northwest Database Society colloquium. Today we're excited to have with us Pat Helland. Thank you for joining us. So Pat is actually one of the founding fathers of the database community, has been doing database work since before, I think everyone here, except maybe two of us, have been born. So very exciting work. He's currently working at Salesforce, doing all kinds of exciting database work there, but has also worked at Microsoft, at Amazon, doing, and you have a lot of accomplishments, but just to kind of name a few things. So at Microsoft, he was chief architect of Microsoft Transaction Server and the distributed transaction coordinator, which I think is very important context for today's talk. Also working at Microsoft SQL Server, but also working with Amazon on scaling, a lot of their services, so a lot of kind of around scalability of database systems, and also working then again back at Microsoft under structured streams in Cosmos. So a lot of exciting work in this space along with this career. So we're just really happy.
Well, thank you.
To be here. Thank you.
Thank you. I like to say I'm very extinguished. So I'm Pat. I'm pretty informal. I dropped out of UC Irvine in 1976 because I had an instant family and had to get a job. But I've been fortunate to get into this area and passionate about databases and passionate about building systems and learning and teaching. And so this talk is one I gave as a keynote 1.5 years ago. So I will kind of talk about technology trends. It's 18 months out of date. Okay, but that's not too bad. Okay. And so the talk is called I'm So Glad I'm Uncoordinated. And coordination is increasingly painful. And what can we do as system designers and academics to think about that? My ideas. I work for Salesforce. I love working for Salesforce. I'm building fun, complex stuff with brilliant people. But these are just things I think about to bore my time. Okay, so I have always been uncoordinated. Seriously, I drop things. I can't catch moving objects. Little League was horrible. 1962, you got to go stand in the baseball field. I didn't mind being in the outfield, but when they wanted me to get in the way of the ball, that was scary because it was going to hit me. I couldn't get the mitt lined up. So I dropped out of Little League and I started reading books and not playing sports. So I'm actually reasonably comfortable with the fact that I'm uncoordinated. And please never throw your favorite coffee cup to me. I will try to catch it and you might need to get a new one. Okay. So what is the agenda? I want to cover how things have changed because I dropped out of college and got a job programming in the 70s. And believe it or not, things are the same, but a lot different now. And we want to talk about how things have changed from the 70s to the 2020s. And then I want to introduce an abstraction that I came up with for coordination. I want to try to convince you that the world is the universe is a partial order. And when you try to collapse that partial order partial collapse, that's coordination. Now, if you're in this pickle, how can you actually do things and relax and accept coordination and think about what to do? And then I want to walk through some examples in a section called Coordination in a Stretched Out World. So let's look at how things have changed, 1970s to the 2020s. So my first programming job, I went to work at a company called BTI Computer Systems, and we were doing a symmetric multiprocessor. So you plug these things in, no network, scalable computing, plug in more CPUs, and you could plug 7 CPUs in a shared memory. The memory was shared, and we could get like 5.5 times the throughput. And that was pretty kick-ass for the day, okay? And it was a 15 megahertz clock. Things have gotten faster, okay? And it took 12 cycles to access memory, or 750 nanoseconds. And because there was no cache, we did not worry about cache coherence. It was just coherent. You're going out to the memory, okay? And so that was cool. And a latch and a read and a write took the same amount of time, 750 nanoseconds. So the thing I want you to carry out of that is at that time, 1978, coordination was dirt cheap, same cost as a read. But what was expensive was CPU, memory, storage, and bandwidth. Bandwidth was infinitely expensive because we had no network. Okay, so, well, networking was emerging. Okay, this is, TCP was 4 years old and all this kind of crap. It just wasn't what you did. Now we're getting more and more stuff. Okay, Moore's law is this transistors double. And that's actually a marketing plan for investment, but they pulled it off stunningly well. And so we keep getting twice as many transistors every 18 to 24 months kind of a thing. So you get more CPU, SSD, NVMe, DRAM, and oh my God. And 18 months ago, when I did this talk, the M1 chip from Apple had 50 billion with a B transistors, and I see some 100 billion with a B transistors chips coming out now. This is awesome. when I dropped out of college, I worked on second sourcing the 6502, which had 4,000 transistors. And that was a big deal to make a chip that could do that. 50 billion transistors a chip. Gilder's law says total bandwidth triples per year. More connections, faster connections. 400 gigabit Ethernet now, and that was 18 months ago, 800 gigabits common now, 1 terabit soon. Now, I'm going to pause here for a second. I am agog and over the top thrilled at large language model training, which is supposed to become a $400 billion marketplace in 4 years. And the GPUs are ridiculously expensive and they're starving. And so they're working super hard to lower latency by squandering bandwidth and make more bandwidth. Bandwidth in the data center, in the building, has gone up a factor of 8 in the last 3 years, and I expect it to accelerate. I think 3 years from now, it will be more than 8 times what we see of 800 gigabit per link. Okay, so I'm digressing from the talk. This is stuff I've learned since. You can drop data onto the NIC of a server and go through the top of rack, through the leaf, the spine, maybe even a couple of spines in some of the architectures, down to the leaf, down to the top of rack, and on the other side, first data falls through in sort of 150 nanoseconds now, if it's uncontested. Go look at bandwidth and data center stuff. It's fascinating, and it will impact databases big time because you can get to the other guy's data almost as fast as yours. But latency lags bandwidth, and I'm actually see some counterexamples with what I just said, but on a whole, this has been true forever. Dave Patterson wrote a paper in 2004, brilliant paper, and he observes that latency increases at a rate which is sort of kind of 10x, sort of kind of if you blur and think about it, but that bandwidth improves by 100x to 1,000x from 82 to 2004. And this is just continuing like crazy. It's glorious. It's fascinating. Bandwidth improves by at least the square of the improvements in latency is what Patterson quoted, and I believe this is still going on. Why does latency lag bandwidth? Well, it's an old networking saying. Bandwidth problems can be cured with money. Latency problems are harder because the speed of light is fixed and you can't bribe God. Okay, so we are really to the point where the time to communicate in a data center is dramatically related to speed of light. So waiting for stuff that's far away. CPU cores need data. If you don't feed them, they stall. The farther away the data, the longer the CPU core waits, and waiting is inefficient. And by the way, I just want to digress. If you read the specs for the 3-year-old Apple M1, I haven't looked recently, okay, there are each core, okay, does 6 to 8 instruction ingestions and retirements per cycle. And it has 600 to 800 out of order speculative executions rattling around in its belly. So I want you to internalize that 99% of the transistors are to optimize for cache misses and make them happen faster. Okay, so that is where we're spending money, is to mitigate the latency of the cache misses. Makes sense when I say that. It's kind of cool. So now CPU core, and I'm looking kind of at a 300 gig, clock cycle. It's sort of kind of 0.3 nanoseconds for a particular single cycle. And so that's about 10 microns distance to get to the register on the chip. And so it takes like 0.3 nanoseconds to get there. The L1 cache is a little farther. L1 is per core on the chip, okay? And then that takes, a little bit longer, 3 times as long, a nanosecond round trip. L2 is, now that's where you got on the chip, but not close to the core, and it's shared between them. Yeah.
Numbers, speed of light numbers, or actual measurements? Yeah.
This is what you can expect off of a typical chip at 300 gigahertz. It's typical and it's broad and it's approximate, but these are pretty much what you see, because getting to the cache on the core is faster than getting to the cache that's shared across the cores on the chip, which is faster than getting to the one which is shared across sockets, okay, which is the L3 cache. And that's sort of kind of 25 nanoseconds now. Okay, is this making sense? And it's not perfect numbers, but these are pretty good ballparks. DRAM has been pretty flat at 80 to 100 nanoseconds since I was working on processors in 1993 and 1 and 2. Okay, why? Because it's a capacitor. DRAM, you charge it and then you drain it. They don't get faster. You get more bandwidth, you get more stuff, but each individual access takes roughly that same amount of time. And it doesn't seem like it's going to change. Now, if you're going across an AZ, you're inside a single availability zone, a single building, and you're doing an RPC to another server, that's sort of kind of coming in around 150 microseconds. I can see some 80 microseconds, but they're quite a bit of time to go through the operating system, go across the network, go into the other side, get to something. So getting to another server is sort of 150 mics, maybe 100 mics, depends. Cross availability zones, these suckers are like a kilometer away. And it's sort of a half millisecond to a millisecond to go. It's stunningly cool. I mean, viewing these buildings that are separate buildings and can fail separately as like one thing we can synchronously update, it's fascinating, but it is longer. Okay, think a millisecond ballpark, assuming no congestion. Cross region, now you're going a long ways, 2,000 kilometers, and that's 200 milliseconds. That's a long old time, right? So the ratio between in the register and inside the AZs, 3 million times, right? And if you're going across a distance, it's 600 million times roughly. That's kind of interesting, right? It's farther away. So let's put latency in perspective. And this is a redo. I did this, but it's inspired completely by a paper from 94, 95 with Jim Gray and Tom Barkley, Chris Nyberg, called Alpha Sort, Cache Sensitive Parallel Sort. And they have a strongly equivalent table. Okay. So we're going to look at this. We're going to say, okay, what's the distance in the physical computer? What's the latency in well clock? What's the latency in cycles? Because now we're getting more cycles per instruction than when I was a kid, okay? And what's that ratio? Now, just to motivate it instinctively, so you kind of feel it in your soul, let's talk about human things. And how do I relate to distance and time? If I'm getting data off of my register, it's same clock, same core, 0.3 nanoseconds, takes one cycle. And since you're doing 5 or so, 6 to 8, I quoted for M1, but ballpark 5, that's a lot of instructions. And the ratio, I'm going to call that 1. Let's consider that getting a piece of paper out of my pocket in a second. Takes me a second. I've got that. So that's the basis for a 1. L1 cache, gee, well, that's 3 to 4 cycles, or 1.1 to 1.2 nanoseconds, and it's 15 to 20 instructions if things go well. So it's a ratio of 4. Okay, so what can I get to in 4 seconds? I can get to my desk at work, sitting at the desk, not my pocket, the desk. Okay, cool. L2 cache, well, that's 6 nanoseconds. That's 20 cycles, or about 100 instructions, 20 to 1. I can stand up and go to the file cabinet and get something. Okay, it's kind of the way to think about that. That's when I'm going to the same chip, different core, okay? L3 cache, I'm going across the sockets because I got 2 sockets in my server or something like that. So that's kind of getting close to 24 to 30, and 400 to 500 instructions are about an 80 to 1 ratio. Well, okay, if it's a second to get this and what's 80 seconds, that's kind of a minute and a half. I can go to another floor in the building in a minute and a half, right? Okay. DRAM, that's 80 to 100 nanoseconds, or kind of 1,000 to 1,500 instructions. That's sort of 300 to 1. Where can I get in 300 seconds, 5 minutes? I can walk a couple blocks in the city, right? It's kind of how I can do it rather than getting it out of my pocket. Cross-server RPC, 150 microseconds. Not microseconds. That's about 2 million instructions. Holy shit. Okay, so that's like 450,000 to 1, kind of, sort of, compared to getting out of my pocket. So that's like walking, for 5 days, right? That's a ways away. Going across the availability zones, that's even more. That's like 15 million to 1, right? Or 3 million ratio, or 3 million seconds is a month. So how far can somebody else who's not had back surgery walk in a month? Okay, it's quite a distance. So this is just shocking when you think about that. The distance impacts the opportunity loss. So going back to 1995 and 150 megahertz in that paper, the CPU clock, versus 3 gigahertz today, well, DRAM takes the same amount of time. Then it was 12 to 15 cycles. Now it's 260 to 330 cycles, kind of depends on how you squint at it. And so DRAM is 21 times farther away than it was then. Yes?
It's million, 1 millisecond. Gotcha. And not billion. I thought gigahertz. I see. Confusion.
I don't think I messed the math up, did I? It's cool. You have no idea how much I screw that shit up. Wait till you're my age, it'll get worse. It just gets worse. It's, okay, cool. So anyway, DRAM's getting farther away, right? So Hubble's universe, everything is getting farther away. There's more and more stuff, more and more thinking. We can store more stuff. We can move more data per millisecond. We can think more per millisecond, but it's getting farther away. And if you want to laugh, you can Google my name or look on YouTube for my name with Kafka, because I did a Kafka summit on a paper and a presentation called Standing on the Distributed Shoulders of Giants, and explaining distributed systems by giggling about Einstein and Newton and Hubble and Heisenberg and Schrodinger, but I won't do this right now. Okay. More thinking while waiting for stuff. It's just up and up. It's more and more and more and more the farther away. So it's kind of like Hubble's expanding universe. Everything's getting farther away from everything else in terms of the opportunity loss. So you're waiting to read, you're waiting to write, you're waiting to coordinate. So waiting to read data from far away, it's immutable data, right? There's lots of data each chip. So we used to get a tiny bit of data. Now we go get a freighter load of stuff. We ship large amounts, same amount of time, kind of, just lots of stuff. Waiting to write data that's kept far away. Everything is inverting to writing logs. Everything. The only way you change things in the cloud nowadays is to write a log that describes something changed. And so I haven't written the paper. I want to write one which is called Depending on Appending, because everything is inverted by how you append. And you reorganize it for easy reading later. But waiting to coordinate, parallel activity is important for many things. When can distant activities remain parallel? When do parallel activities need coordination? So what is coordination? I'm going to argue coordination is aligning parallel work. Parallel is cool, concurrent threads, servers, and work. So I've got concurrent parallelism, and I got to bring it together. I got to align it. So I'm aligning parallel work to share data, to control completions, to advance steps. What does that look like? So coordination in 1978, when I had hair and dropped out of college, okay, I had a lot of hair until I had to get it cut to get a job, okay, and so you had these multiprocessors, and they shared memory, and they'd get to a latch, and you had to wait, and then you'd get the latch, and you'd whack on the shared memory, and then you'd give back the latch, okay, and then the next one would like get the latch and whack on shared memory and give the latch back. That was coordination on that symmetric multiprocessor. That's coordination 78. Uncontested latch for me was the same time as a read. Holy crap, that's not expensive, right? Coordination 2022, multi-core latches. I'm going to go to Zookeeper via RPC. Ooh, Zookeeper. We can talk for hours about Zookeeper. I'm not fond of Zookeeper. Or I'm getting to a database via RPCs. Wow, this is a long time. So in 2022, varying coordination delays. Same server is best case 1 to 300 cycles, right? When you're just modifying a latch in memory, if you have it on your core, it's not so bad. If you got to go get it on the next core, can be really, really bad. Remote servers, 450,000 to 3 million cycles, a lot. That's assuming you're not fighting. If you're fighting, good luck, because it goes downhill fast. So how things have changed. When I was a kid, man, coordination was cheap, free. But CPU, memory, storage, bandwidth, they were ridiculously expensive. Now, I got all this memory. If you don't have enough, wait a couple years, you'll have twice as much, right? And storage, I get more, right? And I got lots of storage, lots of bandwidth, and coordination is ridiculously expensive. So is there an abstraction for coordination? What can we do to reduce the pain? And so we're going to talk now about the partial collapse of partial order. My name, my idea. And just so you know, it took me forever to figure out the abstraction. And while I did, I was fiddling with 3-dimensional PowerPoint pointers and graphs. And so drawing these was what I was doing. You fiddle while you're trying to figure shit out? I was fiddling with these pictures to make this work. So let's talk about history in a system. There's lists, trees, DAGs, right? Love DAGs. List is one thing follows exactly one other thing. One parent, one child. Cool. Tree, many things follow one other thing. Everything has one parent, you have many children. Directed acyclic graph, you can have many parents and many children. That's kind of cool, right? Love DAGs, they're fun. There are no cyclic graphs when you're talking about history. It doesn't work for history, okay? So Lamport said, Leslie Lamport, awesome, brilliant stuff. Ordering of events in a distributed system. And he had this paper, seminal, Time Clocks and the Ordering of Events in a Distributed System from 78. And he said, I got these processes and they send and receive messages. That defines the order. It's not clocks as much as the happened before messages. So I got process P, Q, and R, and they're sending these messages. It defines order, partial order. happened before the ordering of events. Stuff at the sending server happened before the receiving server. You can do the transitive closure of that and see what happened before. So partial order, the messages form a partial order, a DAG. Your time is after all that happened before. So here's an example in RPC. The time advances as it goes across, and you can see the clocks advance. I drew those clocks in PowerPoint. That was kind of a hoot too. And so now Newton and von Neumann had this concept of a total order of time. Newtonian time. Von Neumann, read, write, get your memory, do your instructions, kind of the model for everything. Everything is either before or after. And Newton's time march forward uniformly. All the clocks advance together. Von Neumann, one instruction follows the other. All clocks are on the same clock in a von Neumann single server. But Einstein and Lamport have a little bit of commonality, okay? You have before, after, or side by side. And the partial order is a DAG, and things may follow many predecessors. In Einstein, everything has its own clock, okay? And things can be slower or faster, and it's a mind mess, but it's really cool, right? And it's even worse in distributed systems because, you know, the hypervisor might have swapped you out or whatever. It's even less predictable. So the paths through the universe see different durations. So in Lamport, your predecessors happened before. Paths through the network see different durations. It's making sense to everybody, okay? That was a fun animation. I like doing that. So subjectively, I really am the center of the universe. Somebody's got their mic on. Maybe you could turn the mic off. And so if you look from the perspective of one thing in the directed acyclic graph, it's waiting for messages and sending messages. It's kind of lonely other than incoming and outgoing stuff. And so everything happened that way. And I'm going to argue that coordination is reuniting the branches of the partial order. They may be far away, they may be close, they may be far in space, they may be far in time, but when I bring them together, I think that's the definition of coordination. And so the red one, that's coordination, bringing things together. The green one, that's also coordination. Make sense? So aligning multiple inputs can be painful. Aligning time is hard. Aligning distant servers is hard. Okay? So I call this the partial collapse of partial order. The universe is a big place. Earth's small. Computation on Earth is a subset of the computation. I'm pretty sure there's computation going on in the Andromeda galaxy that we won't know about, right? So partial order is smaller than the universe's total order. And Andromeda is sharded from Earth as far as we can tell. And so coordination can be big or small across threads, cores, departments, services. Coordination is fractal. And so this coordination is that partial collapse. And coordination reduces the disorder of the system. It was more disordered until the coordination reduces that disorder. It's all making sense, okay? So now let's go Zen on coordination. What can I do with this? How can I maybe make things better? So I'm going to talk about ways to relax coordination. And I'm going to argue this is a taxonomy I came up with. And there's actually one more that was suggested to me than the 5 I thought of later on. But you can relax coordination by leveraging space, or leveraging time, or leveraging layers, or leveraging equivalence, or leveraging confluence. And the one I don't have in the slide deck is leveraging retirement. Things are going away, okay? And it's good. I will update that at some point. Let's look at space. Okay, great. I can chart. Different space, different coordination. Earth, Andromeda. Thread, private buffer, your thread, my thread, different private buffer. There's space, it's big or small, okay? What does separated by space mean? Well, memory is reads and writes to memory. How do I use that space? Linearizable objects. By the way, I could talk to you for hours about linearizability. It's a brilliant paper and everyone misunderstands it. It's a view from the outside of, I did a request from a client, it got done, and I saw the answer. It is a timing discussion, is linearizability. And it has objects and operations and the timing of remote clients with respect to that object. A serializable database is a notion of concurrent things not noticing each other. They're isolated from each other and serializable. And I argue that from outside of a database, transactions appear at one at a time. And from inside their parallel, I actually think of a database as being comparable to linearizable from the outside. I ask for it and I see it, and they appear to be ordered from the outside. Inside, they can be doing things at the same time, and that's what serializability accomplishes. So that's just sketching space. Let's talk about time. What can I do with time? How can I relax it? Fate sharing reduces coordination. Dependencies on earlier stuff. I actually like to say durability is a relationship. If you and I are in the same lifeboat, you're infinitely durable. Except I'm dead, you're dead. If you're dead, I'm dead. And so you're there all the damn time, forever, until I'm gone, right? It's how I look at it. So speculation defers coordination. Speculation in that chip, speculation in optimistic concurrency control, speculation reduces coordination. Immutable data is one of my favorite things. It coalesces speculation. If I have immutable inputs, I can have functional programming and I can get immutable outputs. And all of these things kind of collapse because it ends up making time disappear because it's immutable. Pre-allocation, important trick. Oh man, it's expensive to get that stuff. Let's go get 1,000 of them. And then I'll use them again. That reduces coordination. Retries after timeout. That's a variant of speculation, right? I'm going to go do it again. And so I'm using time to relax the coordination. And idempotent work is wonderful. I wrote a paper a long time ago called Idempotence is Not a Medical Condition. Thinking about the behavior of idempotence as you work across this stuff. Sorry, I'm very inappropriate. Just, you're chuckling at me. So now let's talk about, oh, by the way, a colleague's wife heard that and said, oh, you wrong title. She said, idempotence, it's not that hard. And so, and so relaxing coordination with layers. Layers of abstraction. You want to avoid side effects across layers. The higher level operations reduce coordination. I really don't care if the microservice fragmented memory or did a monitoring log. A layer of abstraction hides that from me. I can avoid false dependencies. When I was a kid, we thought page locking was a good idea in databases. We learned that's bad because false dependencies come in. How can we reduce that with layers of abstraction? How can I avoid interference by coordinating the externally visible semantics, not the internal implementation details? And again, these are all layering, allows me to reduce the coordination that I see. In commutative operations, that's where you can isolate partial order. CRDTs are good at this and things like that. I can reorder because of commutativity. You guys asleep? Am I waking? Is this making sense to you? Okay. So that's layers. What about equivalence? I love equivalence. I mean, I just think it's fascinating stuff. Good enough. Don't sweat the details. Updates to caches are not atomic, maybe. Relax consistency to avoid coordination. Lots of things that can happen there. What do I do? Well, equivalence means it looks the same to me. A dollar bill is equivalent. It's a dollar bill. I don't care if it's beaten up or pretty unless I'm giving it to my grandkid for a present, right? And bushels of wheat. King-size non-smoking rooms. They're different. Didn't say whether it's by the elevator. It's a king-size non-smoking room. It's equivalent. Are you guys familiar with the notion of a pork belly? You can sell a pig that doesn't exist in the future. In a year, I'll give you a pig that doesn't exist. Well, what is the pig? Well, it's a standardized equivalent. Get 100 of them, average weight, health quality. And if they put them within a parameters, I can talk about a abstract pig and sell it to you. And people in condos in Manhattans will buy and sell them. And hopefully they sell them before the delivery date and they show up in the lobby of the condo building. Okay. And so you have to ignore the differences. What is equivalent to you? And so there's this duality between private versus shared. Private work allocates an equivalent thing. Shared work has to manage the capacity. I'm in the hotel. I've got a pool of them. How do I figure out when they're full? So I have to think about it differently from the hotel's perspective rather than the guest's perspective. And it's a equivalence at some level, but depends. And finally, there's this notion of confluence, which I absolutely love. And I have a paper called Don't Get Stuck in the Con Game, which talks about confluence, convergence, and consistency, and is basically a diatribe about the inconsistent uses of consistency. Okay. Let's talk about confluence. Confluence is a characteristic of some programs, not all. If the order of the inputs does not affect the value of the outputs, this is a typo. The value of the outputs are not affected by the order of the inputs. Okay, again, a typo here on the slide. Property of some programs, same inputs, same outputs, doesn't matter the execution order. You see this in finding the minimum or sorting or searching. There's a set of things that you see this in, right? MapReduce leverages confluence tremendously, okay? And the Calm conjecture's wonderful theory on this. Out of Berkeley, the Hellerstein and Alvaro, for example. Confluence requires a natural order. And that output must be naturally ordered. So then the way you execute it doesn't matter because it's going to fall into the natural order. Massively parallel work leverages confluence. Break it into pieces. The order across the pieces doesn't matter. Execute those in any order and defer the coordination across the pieces. MapReduce, sort, SQL set operations have this characteristic. Okay, that's confluence. So those are kind of the 5 ones I did, and I didn't talk about things retiring and going away and being deleted, but that's another one I would factor in if I redid this stuff. And so now let's talk about coordination in a stretched out world. How am I going to use these tricks to avoid coordination? So I'm going to go through 6 examples. Let's just walk through it. What if I have a per thread memory pool? So the contention for the memory pool is a darn horrible thing. So I have 100 threads in a shared memory environment, and I go and I make a per thread memory pool, and I chisel away at that, and then go back to the shared memory pool rarely. Okay, what does that mean? Well, I'm using space with buffers. I'm using time by pre-allocating. I'm using a layer of abstraction because malloc doesn't care the physical address of the pointer. Because I'm going to give you different physical addresses, but you don't care because of the layers of abstraction. And I'm using equivalence again from the pointers. Okay, so that's one example, but it doesn't really have confluence in this. Massive replication of caches with asynchronous updates. Google search, product catalog for Amazon. How do I make those work? And so I'm doing e-commerce, I'm doing these search engrams, and the updates happen in the background from batch jobs. And there's windows of time when I could get the new, the old, the new, the old, and then they settle out to the new. Okay, and so reads from any replica, retry to another on timeout. Love the tail at scale paper, by the way, you should read that. And the answers can vary. So this uses space because I'm sharding the items, uses time with retries, it uses layerings for items in the cache, and it uses equivalence because stale is okay. I don't really care if it's the old or the new version, they're equivalent. Reduce CPU core cache misses, speculative execution. I'm running ahead to try branch prediction, and I'm touching the cache lines to bring them close, okay? So that uses time with speculation and layering because caches versus the actual sequence of instruction execution. And so that is an interesting example of using 2 of these tricks to compose a way to avoid coordination. Is this making sense when I say this? Okay. So record-oriented relational databases. I have lost a lot of hair building these moments, okay? And so you're doing record locking transactions, page locking in the belly of the database, right? You're caching data inside the database. You're doing set-oriented operations in SQL, right? Disordered execution. We play all sorts of tricks about reordering set manipulation. You allocate big blocks from shared memory. So I'm using all these tricks. I got space, I got time, I got layers with records and blocks, I got equivalence with memory allocation, I got confluence with set operations. All of these tricks come into play. Internet search operations. I'm calculating the n-grams from a search pattern to come together to find the documents which have the matching n-grams, okay? So I ask the search server for shards. I do get pretty good results because they're varying with things in the background. Retry if I need to, like the tail at scale, and I intersect them. And this uses all 6 of the tricks. Space is the shards, time of the retries, layering the interfaces to the shards, equivalence because the context, I don't care if they're stale or new, and confluence because I'm doing set operations on them. Transactional database optimistic updates, okay? You read the database, you assume it's not going to change, and you go back and say, if it hasn't changed, do this transaction. That's optimistic concurrency control. I thought it was going to fail when I read about it in 81 because I was used to hotspot records. I was wrong, clearly wrong. It's useful. And so that uses space because of the application of the database, and it uses time because of the batch changes, but not so much layering, equivalence, or confluence. So those are the 6 examples. Now I'm going to argue it's expensive to decrease order. I'm going to paraphrase the second law of thermodynamics. Disorder in the universe continues to increase. Why? And you know what I'm saying? You have the gas in here, and if I try to push the gas into one area, it takes energy, right? And so the second law of thermodynamics says it takes energy to reduce disorder. So less disorder here takes energy there. It is easy to break an egg. Pretty darn easy to break an egg. It's really hard to unbreak an egg, right? Okay. So coordination is hard. It takes energy to decrease parallelism. Aligning that parallelism incurs costs in the system. It is easy to branch parallel activity. It is hard to unbranch parallel activity. That makes sense, right? Don't coordinate when you can avoid it. So the takeaways used to be dirt cheap to coordinate. Now it's an increasing pain in the behind to coordinate, and you want to play a million tricks to get out of it. Computing's changed and it's still changing. God, it's fun. Our solutions are changing. We read a lot of immutable data. We write with logs and log structure, and we coordinate. It's hard to pick an authority. It's hard to know a central master. It's hard to do that picking of a single thing. Total order is hard. Coordination is the partial collapse of partial order, which happened before. The partial order in distributed systems is parallel execution. Coordinating, bringing it together, that's hard. So to coordinate less often, you keep stuff isolated in some fashion, some facet, with space, with time, with layers, with equivalence. Equivalence is really fun. And with confluence by allowing them to be reordered as they execute. And so finally, I want to say, I am so glad I'm uncoordinated. And I want you to avoid or reduce coordination if possible. Think about the tricks. For me personally, being uncoordinated has huge advantages. My wife never lets me fix anything around the house because it's a bigger bill to fix it after I try to repair it. So the repair person fixes it and I get to read books and be a nerd. And so that doesn't happen. It's always called the repair person, and my life is pretty good. So I just want to say, that's the end. And I'm pretty good on 45 minutes. I told you 45 minutes.
Yeah. Hey, Pat, this is
Hey,
Dave.
yeah, Dave.
So, I'd like your thoughts on
Wait,
one
Dave,
of,
wait. Magda wants you to wait. Wait. Oh, you want to stop recording the questions? Fine.